Welcome back to Partial Derivatives in Thermodynamics and Physical Chemistry. My name is Kevin Tokoph. Please make sure to like the video and subscribe to the channel for future videos and notifications. In this video, we're going to talk about how enthalpy varies with pressure. And in general, we're going to find that enthalpy at constant temperature really doesn't vary with pressure a whole lot. But first of all, we want to prove that, and then also we want to show how it's used for applications that you're going to see in problems. Okay, so what we're going to do first is we're going to start out with two definitions here. And that's the definition, at least the differential form of internal energy. We know that internal energy, we know that's a function of volume and temperature. So when we write the expanded differential form, du is going to be equal to the partial of u with respect to v at constant t dv plus the partial of u with respect to t at constant v dt. The other thing we have is one other way to express the first law of thermodynamics, and that's that dH is equal to du plus dPv. Okay, so what I'm going to do is on the left side of this equal sign right here, I'm going to make an expression. Both of these sides right here, okay, this side right there is going to be dH. It's going to be something that's equivalent to dH, and then also this side over here is going to be something that's equal to dH, right? Because if I set dH equal to dH, I mean, they're both equal, so I can do that, but I'm going to put a different expression for dH on each side. On the left side, I'm just going to do the differential form of dH, and we know that ultimately enthalpy is a function of pressure and temperature. So when I do the differential, it's going to be partial of H with respect to P at constant T dP plus the partial of H with respect to T at constant P dt. Okay, that's equal to dH. But dH, according to this up here, the first law, is also equal to du plus dPv. So the du component, the du, this right here, I'm essentially going to take all of this, because this is also du, this right here, and I'm going to plug that in right here. So that's this term right there and this term right there. So the du part is going to be partial of u with respect to v at constant t dv plus the partial of u with respect to t at constant v dt. But recall I also have this plus dpv. So the way I do this is sort of product rule for differentials. It's going to be plus p dv plus v dp. Okay? And that's this part right there. So now I have ultimately one form of dH equal to another form of dH. Now what I'm going to do is I'm going to consider the case in which delta T is 0. In other words, I'm dealing with an isothermal system. So if it's isothermal and delta T is 0, that also means dt is 0. So anywhere I see a dt here, I'm just going to set it to 0. And in this case, it's the partial of H with respect to T at constant P, and the partial of u with respect to t at constant v. They're all multiplied by the differential t, so those go to 0. So what I'm going to do now is I'm just going to come down here. On the left side now, all I have is exactly what I want. It's the partial of h with respect to p at constant t dp, and that's going to be equal to all this over here. Now I'm going to do some simplifications, and it may not look like simplifications, but you trust me, it is. This right here, this term, remember that was internal pressure. Okay, that was, and this is supposed to be a pi. It's internal pressure, and internal pressure was also equal to T times the partial derivative of P with respect to T at constant V minus pressure. And since the internal pressure, this thing in brackets, is multiplied by dV, I'm going to multiply this expanded expression for internal pressure by dV. And then I'm just going to tag on the P dV plus V dP. Okay? The next thing I'm going to do, notice that in this brackets, what I can essentially consider is this dV being multiplied to both the P and also multiplied to this whole term over here. So I get that this is equal to T times the partial of P with respect to T at constant V times dV minus P times dV plus P dV plus V dP. Now notice here I have a minus P dV and a plus P dV, so those are essentially additive inverses, so you get 0 there. And now all I'm left with is ultimately the partial of h with respect to p at constant dp is equal to t times the partial of p with respect to t at constant v dv plus v dp. Now, what I'm going to do here is I'm actually going to take this dP, because ultimately what I'm looking for this quantity right there. How does enthalpy vary with pressure at constant temperature? So if I want to isolate that, what I'm actually allowed to do is I'm allowed to divide through both sides by dP. Okay, so that means everywhere I see a differential, I'm just going to divide that by dP. Now notice over here, in this case, I have dP divided by dP. That's just 1. Okay, so that differential is completely gone. However, and also this one is 2. When I divide dP by dP, that's 1. Okay. Now, I have this over here dV over dP. What I have to remember, though, is we're dealing with an isothermal system, so this has to actually be at constant temperature. So that's going to give me this expression down here, which is valid for all substances. The partial of H with respect to P at constant T is equal to T times the partial of P with respect to T at constant V times the partial of V with respect to P at constant T, which comes from this right here, plus the volume. Okay, so the expression that I'm going to use that is valid for any substance if you're trying to find the variation of enthalpy with pressure at constant temperature is that right there. So this is what we'll say is always valid. Doesn't matter what substance you're talking about. Now, one thing I will mention, because it's very important, if you're doing this for certain gases, okay, and in particular, a great example is a van der Waals gas. In another video, we actually see this partial derivative right here. This one right here, notice, is similar enough to when we tried to find the partial of V with respect to T at constant pressure, right? If you think back to the van der Waals gas equation of state, remember that whatever this in the numerator is what you have to solve explicitly for, okay? So the van der Waals equation of state is very difficult to solve for volume explicitly. In fact, it's going to require quadratic formula manipulation and so forth. So this I never wanted to find. Likewise, this partial derivative right here, I also really don't want to deal with. Okay, now I could pretty easily find the partial of P with respect to T, but I'd rather not have to deal with the second one. So what I can actually do is something called the cyclic rule. Okay, this is one of our partial derivative rules that we learned in another video. Essentially what this differential rule says is if I have an equation of state that's a function of x, y, and z, if I take the partial of, let me do this. If I take the partial of x with respect to y at constant z and multiply by the partial of y with respect, this one will be with respect to z at constant x, times the partial of z with respect to x at constant y, it has to equal -1. That's the cyclic rule. So if you wanted to do this for a gas thermodynamic equation of state, you would have partial of P with respect to T at constant V times the partial of V with respect to P at constant T times, let's see, this would be the partial of T with respect to V at constant P, and that would have to equal -1. Okay, so because, notice, right here I have partial of P with respect to T at constant V. That's this first one right here. Then I have the partial of V with respect to P at constant T. That's this, right? So in other words, if I want to find out what these two are equal to, I can actually just divide both sides. I can divide both sides by this differential right here. And that's actually where I get this relation right there. Okay, that's from the cyclic partial derivative rule. In other words, what I can do is I can essentially take all of this right here, these two partial derivatives, and just substitute them with the negative partial derivative of V with respect to T at constant P. And that's what you see down here. So when I do this manipulation, I'm going to get the partial of H with respect to P at constant T is equal to minus T times the partial of V with respect to T at constant P plus V. Now, for the next step, ultimately what I'm going to do is I'm going to multiply by what's termed a fancy one. And the fancy one is just this V over V. I didn't change the value of that term. It's just multiplying by 1 because V over V is 1. The reason I'm going to do that is because one of the relationships we found in the last video that greatly simplifies things is if you have this quantity 1 over V times the partial of V with respect to T at constant P, that's just equal to a constant beta. So basically what I'm going to do is anywhere I see 1 over V, and I've circled this in light blue, 1 over V times the partial of V with respect to T at constant V, I'm just going to take this beta and substitute it in for that. So that means I'm going to keep the negative sign, I'm going to keep the t and this v in the numerator, and so I'm going to get that this derivative is equal to negative t beta v and then plus v. And then notice I can rearrange it to put the minus sign last. V minus t beta v. I can go ahead and factor out the v, and then I get 1 minus t beta times v is equal to the variation of enthalpy with pressure at constant temperature. Okay? Why would, say, this form of the equation, why would this potentially be useful? Okay? Well, this would be useful if you had, if you ultimately had some kind of equation of state, okay, like the van der Waals equation of state, where any one of these partial derivatives, it's usually going to be a partial of volume with respect to something else, like this one I circled. Usually when you have like something like that in a really complicated equation of state, it's going to be really hard to solve just because volume tends to be the hardest variable to solve for. And you don't want to deal with that. So if you can get it in terms of this beta, which is something that they're tabulated and you can look them up in tables, if you know the volume and the temperature, then you can just do this simple algebraic problem. Actually, it's not even algebra at this point. You just plug the numbers in, and that gives you the partial of h with respect to p at constant t. So this is going to be what you would use if you have an equation of state that's really hard to solve for. Okay. Now, why do we care even more about this? Well, there are certain assumptions we can make that can greatly simplify our work. Now, what I want to show you now is actually how enthalpy varies with pressure for an ideal gas. Okay, because most of the problems you're going to deal with are an ideal gas. In fact, we actually just want to go ahead and show dH, the expression for it for an ideal gas, and we'll come across something hopefully that we've seen before. Okay, now just remember what we had originally for this partial of h with respect to p at constant t. If we go back up just to remind ourselves, remember, it was t times the partial of p with respect to t at constant v times the partial of v with respect to p at constant t plus v. Okay, so I just take that down here, and I want to do that for an ideal gas. Now remember, ideal gas is PV equals nRT. This is your equation of state. For this first partial derivative, I want to use the form P is nRT over V. And for the second one, it's in terms of V. I want to use V is equal to nRT over P. Okay. Now what I want to do is I'd like to take the derivative, this first one right here, the partial of P with respect to T at constant V. So what's the derivative of pressure with respect to temperature? Well, this is just going to be nR over V, right? And then if I want to take this second derivative, partial of V with respect to P at constant T, partial of V with respect to P at constant T, what is that? Well, it may actually help you to write this equation of state as V is equal to nRT, because if you're taking the derivative, maybe P to the minus first. Maybe that's a better form to look at it in. And then if you take the derivative, it's just going to be minus nRT, and then it'll be over P squared, because it'll go down to P to the minus 2, pull it into the denominator, minus nRT over P squared. And then you're just going to add on volume, and we're going to simplify this to see what this expression or this derivative is actually equal to. So we're going to have temperature. What's the partial of P with respect to T? That was just nR over V. That's relatively simple. Okay. What is the partial of V with respect to P? Well, it's going to be, you're going to have minus nRT. Now what I'm going to do right here is I have this P squared. Okay. So what I'm going to do is I'm just going to write this as nRT over V, because that's certainly an expression for pressure. And then I'm going to square it, so I'm going to multiply it again. nRT over V. You'll see why I do this in a minute. And then I'm just going to add on volume. That's another term, by the way. This is not multiplying by volume, it's adding it. So notice one thing. First of all, I have an nRT over V here, nRT over V here, so those cancel, right? Those cancel. Notice also I have an nRT right here and an nRT right here. Those cancel. Now, if you were to simplify this further, notice I have a minus 1 over volume. That's just minus V, and then plus V. And that's the expression for the partial of H with respect to P at constant T, and it's equal to 0 for an ideal gas. So anytime you have an ideal gas and you're asked to calculate the partial of H with respect to P at constant T, this expression right here, this is just 0 for an ideal gas. It's almost something you should just memorize, but if you actually had to calculate it or prove it, this is how you would do it. Okay? And what does that ultimately imply? Well, remember that if I integrate everything here, actually let me not even just integrate, let me just leave it in differential form. If I have this dH, it's therefore equal to the partial of H with respect to T at constant P dt. What is this quantity right here, partial of H with respect to T at constant P? Recall that's just Cp, right? Or really and truly, it's actually multiplied by n technically, but it's going to be equal to NCp dt, right? So this is actually the expression for delta H or dH whenever you have constant pressure. It's going to be NCp dt. And consequently, this is also equal to the heat at constant pressure. For solids and liquids, okay, notice we have this partial of H with respect to P at constant T. I'm going to replace that. Notice up here, what we were able to do is we were able to write it like this. So I'm going to say this is going to be minus T times the partial derivative of V with respect to T at constant pressure. And then it's going to be plus volume. And all of that technically is multiplied by that dP that's right there. Okay. So why did I choose to put it in this form? Well, there's a sort of a proof you can do, but we're not going to do that. Instead, we're going to use a little bit of reason to figure this out ultimately. Okay. So here's what we're going to say. We're talking about solids and liquids, so we're no longer talking about gases. If I want to do an ideal gas, I would just do this over here. If I'm doing a solid or liquid, it's a little bit different. So I want you to think about a liquid. This is probably the most intuitive thing. All right, so imagine in the winter, so let's say you live in, let's say it's winter. I'm trying to think of a good place. Well, let's not even worry about the season. Let's say you're in at least Fahrenheit at least, because that's probably what you're most familiar with if you're in the United States. In Fahrenheit, let's say it's about 35 degrees out, so it's above freezing. If you're in a different country watching this, Celsius, it's going to be a little above 0. So I'm just talking about above freezing just to make sure it's not frozen. So you have let's say you have a glass of water, a glass that's like half full of water. Okay, you just have it outside in the cold. So it's 30 degrees out, and let's say that's in the morning. Well, maybe by the end of the day, maybe by about 4 p.m. or something, the sun might have come out a little bit, and maybe there was a little bit of a warm front, and the temperature has gone up to maybe 70 degrees Fahrenheit. So at least in Fahrenheit, that's approximately a 35 degrees. I don't know exactly what that is in Celsius, but the whole point is, if you were to just take that glass of water, okay, and you were to look at the volume of it, okay, other than the evaporation effect, which is a completely different consideration, or, an example is if you were to take a glass of water and heat it in the microwave for 30 seconds and you take it out, did the volume really change? Really? So in other words, if you just leave a cup outside, if I live in Texas, so if you have it out in the morning at 78 degrees out, by 4 hours later, it's 90 degrees. So you increase, 13 degrees or whatever that is. I don't know exactly, 13 degrees, and the volume really doesn't change other than water that's evaporated. But if you were to neglect evaporation, if that didn't exist, you would find that if you raise the temperature or lower the temperature, the volume of the fluid really doesn't change. Okay, and it's the same for solids. So what we more or less say, and it's more of an approximation because there is a very small contribution of change in volume when you change temperature, but for the most part, we just consider this derivative basically as being 0. Okay, it's an approximation we're willing to take because we're still going to get a relatively good answer. And so what that means ultimately is that we're only concerned about this, and that's just V dP. So if I want to figure out what dH is for a solid or liquid, this partial of H with respect to P at constant T dP just becomes V dP. And then I'm going to add on this term, and we already know that that's Cp dt. Okay? for a liquid or solid, there really isn't a good equation of state to relate volume and pressure, so this just becomes V delta P, so P2 minus P1, because technically volume really is not a function of pressure, and then this will become Cp delta T, or if it's dependent on if heat capacity changes over a long range of temperatures, you just integrate this. But these would be your two expressions for solid and liquid, for solids and liquids, okay, for variation of enthalpy with pressure at constant temperature. One thing I just want to remind you is if this for an ideal gas, partial H with respect to P at constant T, okay, this is 0, okay, it is. However, if this is not an ideal gas, if it's a van der Waals gas, hard shell model perhaps, then this is not going to be 0, and you actually have to go through this partial derivative and calculate what it ends up being, and it probably will not be 0. Okay, so in another video we'll actually do a practice problem with mostly gases. That's what we're going to look at, of how to calculate enthalpy changes using the differential form of enthalpy, the method we did here. I hope this video helped you. See you in the next video.